Hi, in this video we're going to look at some derivative shortcut rules that allow us to combine derivatives of different functions that we know. So we're going to go through 4 of them here in this video. There's one more that's in a later section of our textbook, just so you're kind of aware that there will be one more that you'll want to add later. Alright, so just to kind of make sure that we are clear about the notation and what the notation is saying, this first box that I have here, I've got this d dx, and so we've talked about that in previous videos, but what that means is that that's telling us that we're taking the derivative with respect to x of whatever's in the parentheses. And then what we have here in the parentheses is c f of x. And so what we want to be sure that we understand here is what that notation means. So that c, generally, unless it's indicated otherwise, a lot of times in mathematics, c represents some constant, and then the f of x is some other function. So constant times a function. All right, so I'm going to write the rule down here, and then in the next video, there's proofs of a couple of these rules. All of these rules can be proven just using the limit definition of the derivative, but in this video, I just want to focus on sort of memorizing those rules, and then in the next video we'll look at justification of those. All right, so this says that if I'm going to have the derivative with respect to x of a constant times the function, what I end up with is just that constant and then times the derivative of the function. In essence, you can sort of think about almost like factoring that c out. And when you actually look at the proof, that's exactly what happens in the proof, is that that c gets factored out. So key thing there is that that constant just comes along. Notice that's a little different than just find the derivative of a constant function, which we looked at in a previous video, but this is constant times a function. So out to the side here, I'm just going to write a little example. If I have a function, say y equals 3 times square root of x, and I want to take the derivative of that, what this rule says is that the derivative, I'll just use the dy dx notation here, is going to be 3 times whatever the derivative of square root of x is. All right, so in order to think about the derivative of square root of x, I'm going to rewrite this original function as x to the 1/2 power, so I can use that power rule. So up here at the top, I've just rewritten the original function, and then notice I'm using good notation here. Down here below, I've got dy dx equals. So I'm not saying that the function is equal to its derivative. I've got the function labeled clearly and its derivative labeled clearly. All right, and so then I'm just going to use my power rule to take the derivative of x to the 1/2 power. So I'll have 1/2 x to the, and then my power is going to be 1 less. So 1/2 minus 1 will be negative 1/2. All right, so there's my derivative, and of course if I want to simplify that, I can go ahead and multiply the coefficients out front. 3 times 1/2 would be 3/2, and then x to the negative 1/2, I could rewrite that as square root of x on the denominator. So those are equivalent expressions that I have written there, 3 times 1/2 x to the negative 1/2, or 3 over 2 square root of x. All right, so we'll look at some more examples later of sort of combining these rules and putting them all together here. All right, this next rule, just looking at notation here, I've got derivative with respect to x of, and then here I've got a sum of 2 functions. So this is sometimes called the sum rule. All right, so derivative with respect to x of a sum of 2 functions is just going to be the derivative of the first function plus the derivative of the second function. And again, the proof of that just uses that limit definition of the derivative, and you just kind of go through the steps, and this is what falls out the other end. But for this video, we want to really just focus on memorizing and using those rules. All right, so a little example out here to the side. If I have y equals, say, x squared plus square root of x, so 2 functions that I know how to take the derivative of, then dy dx is just going to be the sum of those 2 derivatives. So the derivative of x squared is 2x to the first, exponent decreases by 1. And then when I take the derivative of square root of x, I want to make sure I'm thinking about that square root of x as x to the 1/2. So whether you rewrite that square root of x as x to the 1/2 or not, that's how you want to think about it when you take that derivative. So derivative of x to the 1/2 is 1/2 x to the negative 1/2. And if you don't care about simplifying your answer, you could leave your derivative answer like that. If you want to simplify it, you might rewrite that as just 2x. You don't necessarily have to write that 1 exponent. And then that second term you could rewrite as 1 over 2 square root of x if you want to rewrite that. Okay, so sum rule, I'm just going to take that derivative by taking the derivative of each term. That's pretty straightforward. All right, these next two are much more complicated, and so I want you to be sure that you focus on understanding these rules and understanding when to use these rules. This next one here is for the derivative of a product of functions. I have f of x times g of x. This one's called product rule. And this one might take a little bit of effort to memorize. It's not quite as simple as those other two derivative rules. All right, so I'm going to write it over here to the right, and then I'm going to talk about how I think through remembering it. So if I have the derivative of a product of two functions, then that is equal to f prime of x times g of x, not prime, just g of x, plus f of x times g prime of x. All right, so I tend to think about this rule in terms of words, and that probably has to do with however I learned it. But the key thing here is that you have a product of two functions. And so what I've got here in this first parentheses is really just the derivative of that first function. So I will say to myself sometimes the derivative of the first function. My first function is the f of x times the second function plus the first function times the derivative of the second function. All right, and so again, this is not a proof of this rule. The proof is in the next video, actually, and you use that limit definition of the derivative, and this is just what falls out the end. But it's important to understand when you're doing product rule that it's not just the product of the two functions' derivatives, that there's really two terms here in this derivative. And notice that in each of these terms, you've got the derivative of one of the functions times the other one. And so there are a lot of different ways that this differentiation rule can be written, because you can switch the order on multiplications and you can switch the order on things that are added to each other. So you can memorize this in a lot of different ways. This is just how I learn it, and this is what falls out when you actually do the proof of it as well. So that's kind of handy. In that next video you can look at that. Let's look out here to the side at one simple example, and then there are some examples in later videos. So let me just scooch over here. All right, so if I have a function, say y equals x squared times e to the x, so two functions that are times each other. All right, then when I find the derivative, dy dx is equal to, I'm going to do the derivative of the first. So the derivative of x squared is 2x times the second function. So just the e to the x function, derivative of the first times the second, and then plus the first function, x squared, times the derivative of the second. All right, and e to the x is that kind of unique function that is its own derivative. So we'll look at some examples later where we have functions that's not the same as the original, but it's important to notice that that e to the x function I wrote there at the end is actually the derivative of the e to the x function. This product rule is important to memorize and be sure that you can use it. All right, and then one more that we're going to go over today. This next one here is called quotient rule. And it also perhaps requires some memorization. There are all kinds of mnemonic devices that you can use to memorize it, and so you can look those up. There's a song, quotient rule song. If you like that kind of thing, look that up and watch a video about that. But I tend to just memorize it in terms of the sort of the visual cues that I see here, rather than verbal cues like in a song. All right, so when I write this down, it's going to be important on this one that you've got a few things in the right order. All right, so the first thing I'm going to write down is the derivative of this top function here. So f prime of x. I'm going to write some words up here above that. So I'm going to have the derivative of the top function, the numerator, the f prime of x. All right, and then that's going to be times just the bottom function, not the derivative of the bottom function, just that bottom function. Or like in the previous product rule, I talked about first and second functions, and that kind of works here as well. The first function being the top one, right, the one you see on the numerator of this fraction. Derivative of the first function, or the top, times the bottom. All right, and then on this one, we've got a minus. Notice that I'm really following pretty much the same pattern that I have in product rule up above, except in the middle here for quotient rule, I've got a minus, whereas in product rule, I had a plus. All right, so derivative of the top times the bottom minus, all right, and then I'm going to have the top function, that's the f of x, and then times the derivative of the bottom, g prime of x. Okay, notice that what I have written here so far really matches product rule. And so if you learn product rule in this order, then quotient rule really matches that. Order is important for some of quotient rule. The other thing that's important for quotient rule is that that's not all there is. There is a denominator, and the denominator is the bottom, the g of x function squared. All right, why does that work? Because that's when you apply the limit definition of the derivative. That is what falls out from applying that definition. With quotient rule, I mentioned this, but because you have subtraction in the middle with quotient rule, the order is important. So the order of these two terms on the numerator is important, and one common mistake that students make is getting those in the wrong order. So you just want to make sure that you know those in the right order. Within those terms, multiplication is commutative. So within this first term, you could switch the order of those two things that are being multiplied, but it is important when you look at the order on the subtraction here that you have those in the right order. Okay, I'm not going to do a quotient rule example in this video, but in the next couple videos, there are some examples of quotient rule problems, so be sure you watch those. But for right now, be sure you've got this quotient rule written down correctly and work on learning to memorize that.